This is the second 7.1 video. This is to get you going on some of the more challenging problems. And for the beginning of a chapter, these can definitely get challenging. So I'm actually going to start with number 11, which was one that I ended up not assigning in the beginning set because it's one that doesn't look too bad, but it turns out it's more complicated than you think. At least the only way that I know of to be able to solve this one or simplify it, okay? What we have when we have fractions, and then this is a reciprocal, which of course will create a fraction when we convert everything to sines and cosines. That's what makes this a little bit complicated. So I am going to start out with expressing secant as its reciprocal function, okay? And the problem I have now is that I've got a fraction minus something else that doesn't have a common denominator. And what I really need is I need to be able to combine these terms so that then I can kind of flip and multiply. I could look at this as sine over 1, in which case I would flip it to be multiply by 1 over sine. But I need this all under a common denominator. So I actually can get that if I multiply this by cosine of theta over cosine of theta. That's 1. And what I end up with is 1 over, I'm going to actually write this, basically I'm going to get the same denominator now. I'm going to get everything over cosine of theta, and I'm going to get 1 minus cosine squared of theta. This is going to become cosine squared of theta over cosine, 1 minus this. Okay, so that's what I'm going to get in my numerator over sine of theta. And then before I flip and multiply, I have an identity that I can swap this guy out for, and I definitely want to do that. I'm going to call that sine squared of theta. That comes from sine squared plus cosine squared equals 1. So sine squared theta over cosine of theta, and now I'm going to flip and multiply this times 1 over sine of theta. Okay? And now this becomes as simple as saying a squared, right, over b times 1 over a. I mean, this is just the square of this, so one of these is going to cancel one of these. That's exactly what I'm going to do here with sine. This sine is going to cancel one of these, leaving me with just a first degree sine of theta over cosine of theta times 1 over 1. And of course, that leaves us with the simplest version, tan of theta, okay? So there is a homework problem, I believe it's number 18. It's very similar to this. This gives you a good heads up with how to work that one, okay? I'm going to do one more. I think that could be a challenge. Actually, several of these could be challenges. This would involve converting everything again to sines and cosines. And I've got 1 plus cosecant of x over cosine of x plus cotan of x. We have a little potpourri here of identities. We want to simplify this, okay? So again, I'm just going to start breaking everything out in terms of sines and cosines. This is going to be 1 over sine of x, and I'm going to show you a little trick with that 1 here in a second here, but I'm going to do cosine of x plus cotan is cosine of x over sine of x. Okay, now I'm going to tell you right now, we like ones, okay, when it comes to combining fractions, because this 1 here, I can think of a 1 as anything over anything. I'm going to call it sine of x over sine of x. There is the same thing as my 1. And I hope you see why I did that, because now I have common denominators. So my top here is going to become the sine of x plus 1, sine of x plus 1 over sine of x over, now I have to deal with this, and to get a common denominator, well, I would need to multiply both sides by sine of x, right, top and bottom. So what I end up with down here is sine of x times the cosine of x plus the cosine of x over sine of x. Okay, that's when I multiply this by sine of x over sine of x. That's how I can get everything in the top and the bottom. Now here's another little trick I can do right off of the bat, is that whenever if I have a fraction with the two denominators are the same, I already know that when I flip and multiply these denominators are going to cross cancel. Again, let's look at it this way. If I have 1 over a divided by b over a, when I flip and multiply, I'm going to get 1 over a times a over b, right? The a's are going to cancel, and I end up with 1 over b. So I can that's another little shortcut. If I know how this is going to go, same denominators in the top fraction and the bottom, they're going to cancel when I flip and multiply. So what I have left is sine of x plus 1 over, and then I'm going to factor the cosine of x out of the bottom expression here. So I've got sine of x plus 1 over cosine of x times sine of x plus 1. Okay, well, this and this are the same factor. I can cancel these guys out. I've got 1 over cosine of x, and of course that is the same as the secant of x based on an identity. Okay, so this is definitely about as one of the more complicated ones that I went from here to here, just expressing things in terms of sines and cosines, but using a number of different algebraic techniques to get myself here. Okay, all right, let's look at a few other example problems, and some of these I'm going to just talk about some other techniques you might use to save yourself some time and trouble, other than just automatically always converting everything to a sine or a cosine. Okay, so here's a good example. Always look for opportunities to use identities. This is actually not in the homework. This is just an example problem. Okay, well, with this one, whenever I have a 1 plus or minus a squared function, I should be looking to see if it might work with one of my Pythagorean identities here. So I've already had a long day. Okay, so one of those, as you can see, would be that the tan squared of x plus 1 is equal to secant squared of x. So this here can be substituted with the secant squared of x over the cosecant squared of x. Okay? And actually, this is kind of, we're going to see there's a little bit of a cool pattern when we divide a reciprocal by a reciprocal. One of the things that, if you could think about, when if you remember how reciprocals work, we did this with exponents and some other things, is essentially, rather than rewrite this as a fraction over a fraction, I could think of the fact that the reciprocal is like a hopping of the bar. And so the reality is that I can, as a little shortcut, say, hey, secant squared of x is the same as cosine squared of x in the denominator, and cosecant squared of x is the same as sine squared of x in the numerator. Okay, and I could prove this out if you would like. I could just say 1 over cosine divided by 1 over sine, which means flip and multiply. It's the same as sine over. I'm going to flip and multiply this fraction. I get sine over cosine. So we can algebraically prove this, but I would hope that intuitively this makes sense, that it's really what I'm saying is I've taken that function and I've hopped to the other bar. I've divided instead of multiplied. That's why it's a reciprocal. So this can be transformed into this without having to necessarily write out all those fractions. And then, of course, you should recognize what this is. This is tan squared. Did I switch to x's? I did. Sorry about that. These should have been thetas. Okay. Yeah, not that it really, it's just whatever you start with, you should be keeping up with. I've been doing a lot of x's lately. Okay, there's one simplification. A lot, well, at least a fair amount of steps less than if you had converted everything to sines and cosines, okay? So here's another example. Okay, this one uses another property of reciprocals. This is the secant of x times the cosine of x, okay, minus cosine squared of x. We want to simplify this. All right, well, let's think about this. These are reciprocals. So one thing we know about reciprocals, like let's just say I have 2/4. Well, that's not a good one. Let's just do 5/5 times the reciprocal. I flip it upside down because when I multiply those, I get 1. It doesn't matter what number I start with, the reciprocal will always give me a product of 1. That is a property of reciprocals, and that is the same thing that is true when it comes to trig identities. You should recognize this is going to be 1 over cosine times cosine, but recognize it, notice the pattern, and then you don't even have to write all that out. A reciprocal times a function times its reciprocal will always give me a product of 1. So this is 1 minus cosine squared of x. And voila, we know that as an identity, sine squared of x. And you're done. Okay? So a few little tricks here that can make your life a little bit easier. Okay? I'm going to take another one with fractions. Okay? This one's a little bit more complicated even than the one I did before. 1 plus tan of x over 1 plus cotan of x. Okay? So again, I'm going to start using some similar strategies with fractions that I did before. First, I am going to break these out into sines and cosines. I don't have identities. If they're degree 1, I can't use any of these identities. Okay? So I'm going to do 1 plus sine x over cosine of x divided by 1 plus cosine of x over sine of x. And now I'm going to use that little property I mentioned about 1's being very nice, because I could express 1 as cosine of x over cosine of x, and I could express this one as sine of x over sine of x. Okay, so all I've done is replace my 1's with a form of 1 that allows me to combine these two fractions. And this gives me cosine of x plus sine of x over cosine of x over sine of x plus cosine of x over sine of x. Okay, and we're going to find that similarly to if we have the same denominators, right? Well, if we have the same numerators, I'm going to get a cancellation, but I'm going to show this a little bit more explicitly. If I bring this up, flip and multiply it, I'm going to get sine of x here in the top, and I can rearrange this due to the commutative property, cosine of x plus sine of x. So this is the flip and multiply part, okay? Making this really clear what I'm doing. Well, now you can see that that cancels that, leaving me with sine of x over cosine of x. We know that identity. That is tan of x. Okay? All right. The only way you learn these is by seeing and working a lot of examples. They are definitely a challenge. Okay? Okay, this one says to verify the identity, cosine u over 1 minus sine of u is equal to the secant of u plus the tan of u. Okay, well, this one is not so simple at this point. I could start here, I could start here. I've got a subtraction here. I've got addition here. Given what I have going on, maybe I try expressing this in fraction form and see if I can get it into this form. So I'll try with that, okay? This is going to be 1 over, let's see here, cosine of u plus sine of u over cosine of u. So actually what I have here is 1 plus sine of u over cosine of u. Okay, I don't know. I'm not sure that's going to help me at all. It actually turns out, basically, it's almost like they're saying that these two reciprocals, no, I'd have a 1 plus. So I've gone this far. I could keep going, but my gut's telling me that I think I'd rather work with this side. I'm literally thinking this one the way I would work it on the board. So let's see. I'm going to try simplifying the fraction by multiplying by the conjugate of this. And actually what I did over here gave me a hint that that might be the way to go here. So here's what I'm going to do. I'm going to do the cosine of u over 1 minus sine of u times 1 plus sine of u. That's going to give me a 1 minus sine squared theta, which I'll be able to use over here for an identity. But that does mean I also have to multiply the top by the same thing, okay? So I'm going to keep it in factored form unless I have a reason to break it out. And I'm going to say, hey, this is going to be, going to end up being 1 minus sine squared of u, which will be cosine of u, cosine squared of u, right? I'm going to make sure this is really clear. This is going to be 1 minus sine squared of u. This is a difference of squares, which will give me this, and I'm going to swap it for this identity here, okay? Okay, well, now I'm glad I left this in factored form because I can cancel one of these cosines with one of these squares, all right? And I don't know if you remember, but when I expressed this as, I should have not erased it, actually. I actually have the same thing. I could simplify this as 1 plus sine of u over cosine of u. Okay, so this and this, the left-hand side and the right-hand side are the same. That's considered a verified identity. Okay? All right. I could do one more. If you're not too tired out by all of this, let's just do one more here. Okay? I've got 1 plus the cosine of theta over cosine of theta equals tan squared of theta over secant of theta minus 1. And again, I have a choice as to which one I'm going to work with. I may end up working with both of them. Again, I mean, it seems to make sense, but one thing I do notice that might be kind of cool is tan squared theta is secant squared of theta minus 1. So I could actually, that might get me somewhere here. And if I remember that this is actually a difference of squares, then one of my factors is going to be this, and it'll cancel out. So I might as well do that. I'm going to get secant of theta plus 1 times secant of theta minus 1. That's this term up here. Divide by secant of theta minus 1. And voila, I get that. So this side simplifies to secant of theta plus 1. So I'm thinking this, I can already see like 1 over cosine of theta is secant of theta. So let's see if I can easily transform this into this. Well, I'm going to bunny ear this, okay? I'm going to say, hey, this is 1 over cosine of theta plus cosine of theta over cosine of theta. I am there. 1 over cosine of theta is secant of theta, and cosine of theta over cosine of theta is 1. The left-hand side equals the right-hand side. Okay, 2 more quick examples here, okay? This one is the cotan x times secant x over cosecant of x, okay? I want to use the trick that I used in a little bit of an earlier portion, that if I'm multiplying by reciprocals, and I can only do this if I'm multiplying, I can't do it if I'm adding or subtracting, but that does mean that I just simply hop the bar with the reciprocal function. So I'm actually going to rewrite this as cotan of x, which I could express that. Actually, I will go ahead and express that as the cosine of x, right, over the sine of x. Everything's being multiplied here, so I can do this. And then cosecant of x would come up on top as the sine of x. And secant of x would go down to the bottom as the cosine of x. And guess what this whole thing becomes? This actually becomes 1. Okay? So I kind of like this one as an example. I could have also kept this. Another way I could have gone about this is I could have left the cotan of x alone. And then if I hopped the bar, I'd say, well, cosecant of x goes up as sine of x, and secant of x comes down as cosine of x. And what I have is cotan of x times tan of x, which are reciprocals. Therefore, they multiply to 1, okay? And then one of these I want to do involving even in odd functions requires you to remember that cosine and its reciprocal, secant, these are identified as even functions, okay? And realistically, this has everything to do with the graph. If you remember that cosine has a graph that goes something like this. And if you think about it, it's the one that's actually closer to a parabola. It is symmetric, if it's drawn to scale anyway, symmetric to the y-axis. So cosecant, or cosine rather, and secant, they are even functions that if I put in this, or let's put it this way, if I put in this positive value and then if I put in this negative value, I am going to get the same y value, okay? It doesn't matter if it's positive or negative. So another way I could say is that the cosine of, I guess I can do it here, of negative x is going to equal the cosine of x. And the secant of negative x is going to equal the secant of x. However, sine and a tangent, again, these are graphs that go through the origin, right? I mean, there's going to be, they both have something having to do with going through the origin. They're symmetric to the origin. Therefore, sine and its reciprocal, cosecant, and tan and its reciprocal, cotan, these are odd functions. Therefore, the sine of negative x is going to equal the negative sine of x, okay? It'll be the opposite. If I put a negative x in, I'm going to get the negative value out, the opposite value. Same thing with tan. The tan of negative x is going to equal negative tan of x. And it turns out knowing this can make solving some of these equations really, really easy. Okay, so here's an example. I'm going to take number 34 in the homework, and this one says, hey, I've got the cosine of negative x minus the sine of negative x, and I want to verify that this is equal to the cosine of x plus the sine of x. Sorry that I'm running out of room there. Okay, well, let's think about even and odd functions. Even and odd functions would say that the cosine of negative x, that it doesn't matter if x is negative or positive, I'm going to still get the same value. So that's going to equal the cosine of x. The minus the sine of negative x is going to equal the negative sine of x. Okay, and so if I subtract a negative, I'm going to get the cosine of x plus the sine of x. And of course, that's what I had over here. When I get the left-hand side to equal the right-hand side, I have verified this identity. And yes, a number of times when you notice that negative x in there, use the even and odd properties. Very, very simple to solve these. Okay, so that should give you everything you need to be able to do the homework, and I will see you in class.